Hey, we are going to do a whiteboard problem 8.2. A child sitting 1.1 meters from the center of a merry-go-round moves with a speed of 1.2 meters per second. I'm going to start making my list of givens here while we read this. So my radius is 1.10 meters. The speed v is 1.25 meters per second. Draw a free body diagram of the child, apply Newton's second law in the RZ direction, and then find the coefficient of static friction required to keep the child seated. And we also know the child's mass is 30 kilograms. Spoiler alert, we don't actually need that. Okay, so let's go to our camera. All right, so that's what we're given. So our picture, right, you don't see these merry-go-rounds that much on playgrounds anymore, but they usually have like some kind of handrails there, and they're spokes in many directions, right? So they spin around, and you try and go faster and faster till you can throw your friends off, which is probably why you don't see them anymore. Okay, so we have a person, a child sitting here. So that's the feet and hands. That's the feet. That's the head. Sorry. Okay, and then the child is 1.1 meters from the center. And the speed of the child as it's going around is 1.25 meters per second. Okay, so we're going to draw a free body diagram. So I'm just going to take a side view like this of what the forces are on this child. Okay, so we have the force of gravity going down, Fg. We have the normal, right, the merry-go-round pushing back up on the child, that's the normal. And then it's going in a circle, right? So if we think of a top view here, this is our top view. And here's our child, and we're executing circular motion here. So we know there has to be some net force pointing toward the center, just like our buggy. Okay, and what that happens to be on this is the force of friction, right? And if there was no friction, our child would just get flung out. Or if we start going too fast and friction can't keep you seated, then you're going to get flung out too. That's when the fun happens. Okay, so we need to set up our coordinate axis. So that's our R direction, radial pointing toward the center of the circle, and Z is perpendicular to that. Okay. So if we look at it this way, right, this would be our Z, and this is R. Okay, so let's apply Newton's second law. Oh, we forgot to say that we want to find static friction required to keep the child seated. Newton's second law. Okay, so we have the sum of our forces equals mass times acceleration. We get our forces from the free body diagram. First thing, we're just going to write them all down, plop them down, not worry about directions. We're just keeping them with the vector on top. Force of friction is mass times acceleration. Okay, now we can break them into column vectors. Okay, so and we're going to write this now as R and Z instead of X and Y. So force of normal doesn't have any component in the radial direction. It has 0 there, and it's positive in the Z direction. We have gravity, again 0 in the radial direction, minus Fg in the Z direction. We have the force of friction in the radial direction and 0 in the Z direction. And then again, mass is a scalar, so that just comes in and multiplies both components of my acceleration. So MAR, MAZ. Okay. My Z acceleration is 0, right? So the child is not accelerating up or down off the merry-go-round. And my radial acceleration, we know if it's undergoing circular motion, radial acceleration is v squared over r. Okay, so we're going to plug that in. All right, so now we can break out our two equations, right? So our top row is one equation and our bottom row is another equation. So the top row, our radial direction, gives us that the force of friction is MAR. Force of friction is mu times the force of the normal. And our radial acceleration is v squared over r. Okay, and then on our z direction, that's our bottom equation. We get the force of the normal minus force of gravity equals 0. So force of the normal equals force of gravity. This equals mg. Right, so we get force of our normal equals mg. All right, so now that we have normal, we can bring it in, plug it in over here. And so our z equation becomes mu times mg for the normal equals mv squared over r. Our mass we can cancel out on both sides. We're solving for static friction. So we get mu equals v squared over r times g. So we can plug in now. We have 1.25 meters per second for the velocity. That's going to be squared. Our radius is 1.10 meters. And g, surface of the Earth, 9.8 meters per second squared. And if we calculate that out, we get that coefficient of static friction here is 1.45. Okay.